Hello to everybody. For the subject Industrial Robotics in Universidade de Aveiro, Portugal, I developed a graphic interface to control the kinematics of the robot SDA10F. First, I want to show you the help window, where you can find all the information about the robot and this project. As we can see, there are shown the joint limits, the DH matrix used for the direct and inverse kinematics, and the equation used to determine the value of the rotations needed to reach a certain point in the workspace. And also we have a picture of the studied robot. The first step to work with the interface is to configure it by specifying the paths for your STL models and for the MATLAB functions used in the code. As you can see in the context, it will show that you are on the right folder. Once the configuration is already done, we can start the interface. We can start talking about the visualization part. As we can see, we can change the visibility of the robot's parts, the robot skeleton, the coordinate systems, and the tables that will be used in a future simulation. Finally, we have an animated gripper that's shown if it's opened or closed, and we can also change the scale of the coordinate systems as we prefer. We can set the duration of the movements and the color and visibility of the trajectory points of the end effectors. We can also define if we want to work in radians or degrees, at least for the direct kinematics. In the below part of the interface, we can see the transformation matrix, one for each arm, that will always show the position and orientation of the end effectors. Now, we can finally continue to the kinematics part. As we know, the direct kinematics works by giving the robot the final rotational values we want for each of the joints. So we can try these default values. Now we can go back to zero hardware position. And now if we write a value that exceeds the limits defined, it will saturate to its maximum and move. Once again, we can return. Well, so we can continue to the inverse kinematics that are a little bit more complex. Here we can define a position and orientation we want for the end effectors to go. Of course, each arm works individually, so we can define different values for each. As we can see, it works perfectly, and we can see that the end effectors are in the position that we wanted, as shown in the transformation matrix. Now, it's obviously that the robot can't get to a point that it's outside of the workspace. If we try this, he just can't do, and will show a warning about the set point that it's impossible for him to go. And it's also important to know that there are some points inside the workspace that can't be reached with all the orientations, so we must be careful with our set points. In the below part, we can also find two more information fields, with the actual orientation values of the joints, rotational values of the joints, and the verification of the joints limits. As we can see, the limits field now is filled by zeros, telling us the node of the joints had exceeded their limits. This might change now if we try to get to the same set point with a different redundancy. As you can see, the second redundancy to get to the same set point will provoke collision, and the second joint of each arm would exceed the rotational limits. So, as we can conclude, not always is possible to use all the redundancies of the robot, so it's better to use the control limit switch that will warn whenever a movement is not possible. Now, I want to show you two quick demos using inverse kinematics. As we can see, the robot gets to the defined point with no error. But the movement between each point is not linear, and that's why it's important to use differential kinematics. The inverse of the Jacobian of the robots allows us to use linear movements. Anyways, it will introduce some error because of the variation of the rotations while using the same Jacobian for each step. For lack of time, I couldn't or I wasn't able to develop the control movement with differential kinematics in the workspace, but as it's already implemented in the code, I'll show you 2 demos of the linear movements we can get with it. As we can see, there are linear, horizontal and vertical movements. Well, finally, the most important part of the project was to use the different movements to the robot, the different movements of the robot in order to simulate an industrial process, as we will see in the simulation part. We can define if we want to see the end effector's trajectory points before every movement and compare them with the actual trajectory points. Obviously, we may turn on the tables. First, the robot will get from 0 hardware to a starting position predefined, near the working tables. As soon as the parts arrives, we will assume that we have sensors and vision systems, so we can determine the random position and orientation of the parts above the tables. Then, once again, the robot will make an approximation movement to the parts, leaving a difference in Z equal to 50 units, correcting the orientations of the gripper. Then, we will use a linear approximation to the part and the gripper will close. The robot will go up with a linear movement, then place the parts in a near position and join them with a linear horizontal displacement. With direct kinematics, we can get the joint 0, the body of the robot to rotate 180 degrees, and finally, it will go down, open the gripper and go up, all with differential kinematics. The last movement contains the leaving of the already joined parts, the returning of the robot to the initial position, and, if the cycle is not ended, the entry of new parts. I hope you liked this video, and well, I'll leave you with a few more cycles of the process. Thank you so much, and see you next time.